We're happy to have with us for our conference this year Dr. Danny Faulkner. He is with Answers in Genesis, and he's an astronomer. And I was trying to find someone that would be a great complement for this conference. We haven't had too many astronomers here. And so I was recommended that Danny Faulkner would do a great job for us, and we're glad to have him. So, Dr. Faulkner, God bless you as a minister to us.
Well, good morning. I'm delighted to be here. Thank you for inviting us. My wife Lynette is with me. It's our first time to be in Northern California. We've been to Southern California a number of times. It's a bit different up here. So anyway, we're enjoying it, and thank you again for having us. I want to talk about big problems for the Big Bang. This is the dominant cosmology. It's been dominant cosmology for a half century. I want to define the word cosmology for you. It's a study of the structure of the universe. More technically, Big Bang is technically cosmogony, which is the study of the history and the origin of the universe, but so many people today just kind of convolve those two. But cosmology should be the study of the structure of the universe. And there are many different types of cosmologies. The idea that the Earth is a sphere is a cosmology. The idea that we go around the sun every year, that's a heliocentric theory or heliocentric cosmology. Any statement about the world as a whole like that is a form of cosmology. Of course, one about the entire universe is among the biggest of cosmologies. And these ideas are not new. We saw in the previous talk tracing back to the ancient Greeks, and we go back to the ancient Greeks in much of what we do in astronomy. And they had this idea that the Earth was at the center of things, and then it was surrounded by this crystalline sphere, this transparent sphere here, with stars impregnated on them. In fact, the sun would move around on that as well, separately from the stars. The stars would remain fixed, but the whole thing would spin around us. We call this the celestial sphere. When I taught at the university for many years, we had half a dozen of these in the lab, and I had a couple of lab exercises I did with my astronomy students. So before I left the university a few years ago, I went in and took a photograph of this, so I'd have a good picture of this model. And it's a very useful model, but it's not a true model, I don't think. But we can use it, and we use it all the time in astronomy. Again, the idea that the stars are impregnated on some hard, transparent sphere. And they even had a word for that. The Greeks called it the stereoma. That was the word they had for it. And that was that, again, hard structures out there. And if you had been taking an astronomy class 2,000 years ago, this would have been presented as truth. This is the way the world works. This is our cosmology. Now, there have been a number of attempts over the years to wed Genesis creation account, when it comes to astronomy particularly and cosmology, wed it to the current thinking of the day. I'm going to give you 3 examples, and each one of them, I think, ends in disaster. So it's a good lesson to us not to take the secular cosmologies terribly seriously. We should evaluate them in terms of Scripture rather than the other way around. So the first attempt here is this word rachia. It's a Hebrew word that occurs 17 times in the Old Testament. It occurs 9 times, more than half of those times, just in the creation account itself. And it's a difficult term to try to describe. It's something that's been spread out or hammered out or beaten out. A lot of people get off the tracks on this. The thing is, it's a noun that comes from a verb which means to spread or beat things out. For instance, gold would be a good example. It's very malleable. It's a tough word to say, isn't it? And it means mechanical means you can press and roll and spread gold very thinly. So just a few atoms thick. You can see the light shining through it, and you use that for inlaying things and gilding things. Well, the rachia is first mentioned in the day 2 account in verse 7, this thing that God says that he made on day 2 to separate the waters below from the waters above. And in the God, it says in verse 8, I believe, called it heaven. He said he called this thing the rachia, he called it shemayim. Shemayim is the Hebrew word translated properly as heaven. Now, when the Septuagint translators came along, this is around 250, 300 BC, they were translating the Hebrew Old Testament into Greek. At that point, a lot of Jews, particularly that have been spread around the world outside of Judea, they didn't read Hebrew anymore. And so they wanted to put it in the language they could understand, so the Greek was the common language even at that point because of Alexander the Great's influence. And when they got to this word rachia, they translated it stereoma. You see what's going on here? They were saying, okay, this thing that God made on day 2 is this crystalline sphere that we now know is the proper cosmology. So they were wedding the creation account to this, excuse me, to the cosmology of the day. Jerome comes along a few centuries later. He's the one who translated the Old and New Testament from the original languages into Latin. It became the Vulgate and was the scriptures for the next 1,000 years until people began translating into more modern languages a few centuries ago. And he translated this as firmamentum. And I'm thoroughly convinced that what he was attempting to do there was to replicate what the Septuagint had done. He got to this word rakia in Hebrew, and he could do Hebrew, by the way. He got to that word and had no idea how to translate that. But he looked at the Septuagint, realized, okay, he was familiar with the Greek cosmology, and so he attempted to translate it in terms of what he thought he knew as well. So he repeated the mistake now in Latin. And by the way, if you look at that word, I think you can see we get the word what from that? Firmament, as well as just shorten it down a little bit more, it's something firm, right? Something hard. Again, getting back to that stereoma. And of course, what happened is early English translations of the Bible, the King James renders it firmament, but they were not the first. There were other people who attempted before that, rendering it as firmament, which was just a transliteration from the Septuagint into English at that point. So the more modern translations tend to translate that as expanse. I know the ESV does, the NIV, I think the NAS does as well. I was very disappointed to learn about 6 months ago that the New International retreated on this. From the beginning of the New International Version, they translated it as expanse. But I think in the 2011 or 2012 revision, they went with vault, which is a horrible translation. As bad as stereoma and firmament are, it's the worst possible beyond all of those, because it gets back to this vaulted ceiling that developed in the Middle Ages. And so they've completely retreated, and I think it's a worst possible translation, as I said there. Okay, what's the difficulties with this translation? Well, it gets people thinking about this rachia all wrong. When they thought stereoma and then firmamentum and then firmament and now vault with some translations, you tend to think in terms of Middle Eastern, ancient Near East sort of beliefs and ancient cosmologies, and it's completely wrong to do that because I think the Bible predates all of those and gets the truth, whereas the others are pale imitations at best. And it was the error, I think, was driven by an attempt to accommodate the cosmology of the time. They were so convinced that the cosmology of the day was right, then they felt okay in going ahead and interpreting Scripture that way. And again, you should be interpreting the cosmologies in terms of Scripture, not the other way around. Here's a 1475 woodcut showing the idea that developed in the Middle Ages. You have the Earth down here, and then you have the moon and the star, Mercury and Venus, and the sun, Mars, Jupiter, and Saturn are like bright stars. Then you have the this is the firmament here, I think, going up through, and the stars up there. I guess the heaven up above there was their idea, and there's the earth down below. And this, again, was accepted widely from the ancient Greeks through the Middle Ages. And, of course, that sort of fell apart in more recent times because nobody believes that kind of cosmology anymore. Number 2, attempts to wed Genesis to cosmology. We had this man named Claudius Ptolemy who lived 19 centuries ago. He wrote a book, a very famous book we now know as the Almagest, and it's a compendium of everything known to the ancient Greeks about astronomy. It's a treasure trove of ancient Greek ideas about astronomy. If we didn't have that, we wouldn't know much about what they taught back then. Also, he gives us the constellations as we know them, the 48 original ones. Really a wonderful book. But he also, it's best known probably and was best preserved for the fact that it had what we call the Ptolemaic model. I already mentioned the stars seem to remain fixed. They change throughout the night due to the Earth's rotation. They change throughout the year due to the different seasons we have. As we go around the sun, we see different stars at night. But they come back tomorrow night. They come back next year. When I look up at night, I see Orion. I'm seeing pretty much what Job saw thousands of years ago because the stars, while they're moving, are so incredibly far away that they don't really change over many human lifetimes. However, the sun appears to move through the stars once a year due to our revolution around the sun. The moon takes about a month to go around through the stars due to its orbit around us. And then the 5 naked eye planets, Mercury, Venus, Mars, Jupiter, and Saturn, look like bright stars. I was out early this morning. I could see them out in the due south up in the sky. I could see both Saturn and Mars. They're pretty bright in the sky right now. And they go through a very erratic motion. They generally move west to east with respect to the stars, but then from time to time they reverse and go east to west in a backward motion. So the planets usually go like this. Then they stop what we call retrograde motion, and then they go back forward again. Right now, Mars is just starting to retrograde, will be for a couple of months now. And how do you explain those motions? Well, today we understand we're passing up Mars on an inside orbit, on a smaller, faster orbit. It's like passing a car up on a highway. The car will appear to move backwards, right? Briefly, but it's just because of our perspective. But back in the ancient times, people thought we were the center of everything. And so they thought that all these things moved around us, and they had to have things moving in perfect circles. That was a pagan idea they had. It's geocentric. We're at the center of everything. So this was a very complicated mess. Well, nearly 2,000 years ago, Ptolemy came up with a way to do this. And what you have are the sun and the moon and the 5 naked eye planets move on one circle called an epicycle. And then the epicycle in turn moves around the Earth. And so you get this very complicated motion like this as it goes around, and you can get the planets moving backwards. And what he did is he adjusted the size of the 2 circles involved and the speeds of motion and got a pretty good fit to the data. And so here's a little mock-up of what it looks like. We're showing the Earth at the center, and the red dot is supposed to be Mars. And you'll notice that Mars is going around on this epicycle, this red circle. The epicycle in turn is going on a much larger yellowish-looking circle. That's called a deferent. And this kind of a bluish-white line that connects the Earth to Mars you'll see mark out this position. Those little asterisks over there indicate the stars, and you'll see right here it's going forward. Then Mars appears to move backwards, and then it starts to move forward again. Everybody see how that works? Now, it's not entirely clear what was going on here. I think the pretty good authority of it, I can say this, I don't think Ptolemy was actually saying this is the way the world worked. Instead, what Ptolemy said was he was trying to describe the motions, which is best you can do sometimes in science, and he used the best mathematics available to him, which was geometry. Now today we use algebraic expressions to describe these motions. But nobody would say, well, the algebraic expressions themselves are reality. They're just a representation of description we use mathematically. But somewhere along the line between the ancient world 2,000 years ago on up to the Middle Ages, people lost sight of that, and they began to believe that this was reality. This is the way the world really worked. There really were these little circles and circles and circles moving. Anyway, so what happened is the Ptolemaic model became the most successful theory in the history of science. It lasted 15 centuries. Do you know of any theory in science that can claim even 10% of that longevity? Not many. Newtonian physics has lasted about 300 years, but it was kind of superseded a century ago with modern physics. We still use Newtonian physics, even though we know it's not quite true. And laws of thermodynamics go back 150 years maybe. Electricity and magnetism about that far back. So we've got some great theories, but none of them in terms of longevity even come close to how long this model was widely accepted. And its strength was this: it could be continually modified. You see, after a few centuries, they found a few little discrepancies between the data and the theory. You know how they fixed that? Remember those 2 big circles you had? You could add another circle, and then another circle, and then another circle. And so by the time you get to the year 1600, there were some systems that had as many as 100 little gears and circles and stuff going. You see what's going on here. It gets more and more complicated. So its strength was that you can continually modify it and get perfect agreement with the data. But its weakness was that it could be continually modified. It's both its strength and its weakness. Isn't odd how that works out sometimes. Well, by the time you get to 1600, people begin to realize that this model was crazy because it was just very complex. It was very complicated. And the model couldn't be disproved. You know, if you can continually modify your explanation for something, no matter what new data come up, then is it really a good theory at all? Not really. Anything explains anything and everything explains nothing. And that point was made in the first talk this morning as well. And I thought to myself, I'm going to say the same thing next hour. All right, so it became very complex, and there's this principle called Occam's razor, the Lord Occam in the Middle Ages, who said when it's called parsimony, that means simplicity. Basically, if you're confronted with two different explanations, one very complex, convoluted, and just whacked out, and another one's pretty simple, the simple one's probably the correct one. And so by the year 1600, people were starting to call into question this Ptolemaic model, and eventually they chucked it in terms of a heliocentric model instead. In the year 1600, very few people knowledgeable people believed the heliocentric theory. By the year 1700, almost nobody didn't. Everybody agreed. 100 years made a huge difference in the 17th century. And this was a large part of the problem with Galileo. He came along 4 centuries ago, and he found some things like, for instance, with his telescope, he could see, first person to do astronomy apparently, and he could see phases that Venus went through. And that could only happen if Venus orbited the sun. And obviously, if Venus orbited the sun, why would you not expect other objects to orbit the sun as well? He saw little satellites, 4 satellites or moons of Jupiter orbiting Jupiter. Obviously, orbiting Jupiter, they weren't orbiting the sun. Everything was supposed to orbit the sun. So they began to really throw in some problems that the Ptolemaic model could not explain. And the problem is the Roman Catholic Church by 1600 has, through the work of Thomas Aquinas a few centuries earlier, had taken these ancient Greek ideas from pagans. They were sometimes termed pre-Christian Christians, those fine Christian theologians like Aristotle and so forth, and made their ideas truth. The idea that man's mind had not fallen at the time of the fall, the moral will had, but not the intellect. And so man's thinking would allow him to arrive at truth. And so they taught this, and they wedded it to their Christian teaching. Again, with disastrous results, because once the Roman Catholic Church did this, by 1700, the heliocentric theory was dominant. The geocentric theory, the Ptolemaic model, was out the window. And if you've been interpreting Scripture in terms of that dominant cosmology, then it brought discredit and disrepute upon the church again, didn't it? And we're still carrying the burden of that around with us after 400 years. So again, 2 disasters, people attempting to wed the Ptolemaic model and the stereo model, this crystalline sphere, this celestial sphere, wedding it to our biblical cosmology. Well, as I've said, since 1965, the Big Bang has been this dominant cosmology. It's a belief that 13.8 billion and 5 years ago, they updated that 5 years ago, so it must be 5 years more than now, the universe suddenly appeared. First of all, there was nothing. And when I say nothing, I mean truly nothing. No space, no matter, no energy, and no time. Try to wrap your head around that. And then there was something. The universe suddenly appeared. Now, there's a common belief that, the Big Bang, it's this thing, it's this explosion that took place. That's really a bad name for it. They tried to rename it, but just the alliteration sticks. It's not really an explosion. It's just a sudden appearance of everything in an expanding rate, getting bigger all the time. That's basically what the Big Bang theory is. It's been the dominant theory for 50 years. And many believers out there, these are people I don't doubt their salvation, and I could name names if you wanted to hear them, of people who teach that Genesis creation, in the beginning, 13.8 billion years ago, God created with a Big Bang, heaven and earth. That's basically what they're arguing in all of this. Do you see the pattern going on here? It's repeating itself. They're taking the latest cosmological pronouncements. They're now wanting to interpret Genesis creation just like these 2 previous attempts that led to disaster. And I think the same thing's going to happen again. They argue that it's an effective evangelistic tool. From the ancient world, people thought that the world was eternal. Even at the time of Sir Isaac Newton, who understood the Word of God very well, and he believed very much in creation and a personal creator, but he himself believed in an eternal universe. And I have to say, come on, Sir Isaac, you're far brighter than I am. What part of in the beginning do you not understand? All right? He let his Greek cosmology get the better of him on all this as well. And this belief that the universe is eternal persisted well until into the 20th century. And then when I was growing up back in the mid-60s, suddenly they discovered this cosmic background radiation, which was a prediction of the Big Bang model that the competing steady-state eternal universe theories couldn't predict. And within a matter of like 2 or 3, 4, 5 years, the whole world shifted over to Big Bang. And there was a lot of resistance to this idea for a long while because it posits that the universe didn't exist and then it did. So the universe had a beginning a finite time ago, and to many people, they thought, wait a minute, if the universe is eternal, we're good because there's no place for a creator. But if the universe suddenly existed in finite time ago, that strongly suggests that there's a creator. And of course, that's been changed too. So there was resisted for the longest time, but many Christians now take this idea that the universe had a beginning and hence there must have been a beginner. And they argue, well, who was that beginner? And they try to argue backwards then that this must be the God of the Bible we're talking about. That's where the evangelistic tool comes in. And I understand that motivation. I understand the good intentions. But make no mistake, our evangelism must be based upon truth, right? You can't chisel people with a fable somewhere along the line and then suddenly start claiming truth. You've got to start with the truth and end with the truth. You don't start with the false and then work your way to the truth. So the question is the Big Bang a true theory? Is it a true theory? And is it biblical? That's the standard once again. I wish people in the past had taken the standard when it came to the stereomon, came to the Ptolemaic model. And yet I see, it just breaks my heart, I see people repeating the same mistake over and over again. Anybody know who this is? Photograph of? Edmund Hubble, very good, very famous astronomer, lived in the first part of the 20th century. He had 3 great contributions to astronomy. His first one in 1924 was to prove that other galaxies exist. Up to that point, for more than 45 years, most astronomers thought that our own galaxy, the Milky Way, was it. That was the universe. And it contains a few hundred billion stars, but he showed in 1924 that there were billions and billions, to quote Carl Sagan, of other galaxies out there, and the universe was far larger than anybody had ever thought really before. A few people had, but not most astronomers, as it turns out. So he proved other galaxies existed, but then he followed that up 5 years later with his observations that showed the universe is expanding. What that means is that galaxies are getting farther and farther and farther apart. And the simplest interpretation is that the universe is expanding. This is a photograph of the famous 100-inch Hooker telescope at Mount Wilson. Anybody been there to take a look at it? It's right above in the San Gabriel Mountains overlooking Los Angeles. More significant discoveries were made with this telescope, except for the first one Galileo used. So it's really a remarkable telescope. It's actually more was done with this telescope of foundational importance than done with the HST, the Hubble Space Telescope. It's that important. It's a shame they don't use it for research anymore, but it is kind of outdated, and it's also, lights have really creamed it pretty badly. This is a photograph of the Andromeda Galaxy. It's the closest galaxy of any size to us. You can, on a dark, clear night, you can make it out easily. This is the center of the galaxy. This is a couple of satellites it has. It's a couple 100 billion stars. 100,000 light years across from upper right to lower left. If this, very similar to our galaxy, so if this were our galaxy, we would be about here. You are here, sort of sign pointing right there. About halfway out from the center. Again, we think there's a lot of similarity between the two. Just one of the closest galaxies to us. This is a Sombrero galaxy. This one's really cool. It looks like a sombrero, also called M104. This dark lane across the middle, that's caused by large dust clouds absorbing light of more distant objects. We can't see to the center of our own galaxy, at least not in the visible part of the spectrum because of that dust. This is another type of, these are all called spiral galaxies. I think they're the coolest looking galaxies because of the spiral pattern they have. This in particular is called a barred spiral because it's got a bar running across the middle. Instead of the arms coming right off the nucleus, they're coming off the end of that bar. And there was a debate for a number of years, finally settled about 25, 30 years ago. People were wondering if maybe our own galaxy has a bar at the middle, a modest bar. And turns out it does have that. We just can't see it very clearly, but we have lines of evidence from other wavelengths to show that. I think these are the most pretty galaxies, and I don't know about you, but this morning I feel a lot better about myself realizing that I live in a particularly beautiful galaxy. This is a plot from Edmund Hubble's original paper from 1929. What he did is he took galaxies at the time and he measured what we call the redshift. Redshift is just the spectral lines. We see absorption lines in the spectra of stars and galaxies. These are due to physical processes going on in the stars. And they can occur at a certain wavelength. We know where they ought to be. We can measure those in the lab. But those spectral lines will be shifted generally to longer wavelengths towards the red end of the spectrum due to, could be several factors, but one simple would just be motion. If you're familiar with the Doppler effect, if an object is moving towards you like a siren or an engine of a train or something, and it goes past you, you'll hear the horn go, bow, like that. It's a Doppler effect sort of thing. We don't think it's exactly a Doppler effect. It's something similar to that. But if galaxies are getting farther away from us, then their light should all be shifted towards longer wavelengths, towards the red end of the spectrum. And what he did is he measured here the velocity of recession vertically. Here's 0, 5,000 kilometers per second, 10,000 kilometers per second. Then he measured it versus distance this way. A parsec is a unit of distance equal to roughly 3¼ light years. This is a million parsecs, 2 million parsecs. And what he found was a rough correlation between distance and velocity of recession. The higher this velocity of recession is, the greater the distance is. The lower the velocity of recession is, the lower the distance. You'll find these dots are following a linear relationship pretty well. And he's got some lines drawn through those points. This is a little crude, but you can see the trend, and this was done in 1929. We've since improved upon this tremendously over the past 90 years, and the trend holds up. Generally, the greater the distance a galaxy is away from us, the greater its redshift is. And that, as I said, is a matter of observational data. And it doesn't look so good here, but in modern data, since then, it's gotten better and better and better. What does that mean? Well, I think the most straightforward interpretation is that the universe is expanding. It's getting bigger. The galaxies are getting farther apart. It's not the only possible explanation, but it's the most obvious, straightforward one. And as a Bible-believing Christian, as a creationist, I don't have a problem with that. Okay, I don't have a problem with that at all. Anybody know this guy's name? Georges Lemaitre. All right, he was a Belgian. Well, you can see at collar he's a priest, right? It may interest you to know that a lot of priests are also scientists. He was a theoretical physicist. There are astronomers. I've met some Vatican astronomers, kind of weird at an observatory. They got that collar on, But at any rate, they have a lot of people doing professors' work at different Catholic institutions and so forth. Well, Georges Lemaitre picked up the mantle on this about the time Hubble was doing his work, and he was the first one to take this idea of an expanding universe and ask the question, well, what happened in the past? And he argued that, well, in the past, if things are getting farther apart, if you ran it backwards, you'd find things getting closer and closer and closer together, and eventually it ends up at the time that everything in the universe would be kind of piled up in one heap. He called this little heap, to start with, the primeval atom, or the cosmic egg. And as a Belgian priest, he was a theist. He believed in God. He believed in some form of creation, but he believed in a theistic evolution sort of creation. And he believed in billions of years. And his idea was basically God laid this cosmic egg sometime in the past, and that was a creation event. And from that launched or hatched the universe. And this was a kind of naive teaching that he had back around 1930, but it is considered today to be the first inception of what became known as the Big Bang Theory. It was more formally published 18 years later in 1948, and then continued on beyond that. So the Big Bang, the universe began in ultra-dense, ultra-hot state, and it came into existence very hot, very dense, and it's expanded, and as you expand a gas, it cools. So the universe started off very hot, very dense, but as it expanded, it got cooler and less dense. And after 13.8 billion in 5 years, here we are today in the universe we see. That's the basic story of the universe from the Big Bang perspective. Again, met early rejection because the universe had a beginning. So from 1930 to 1965, it had very few adherents, but that all changed in 1965 with the discovery of what we call the CMB, the cosmic microwave background. There were two astrophysicists working for Bell Labs in the early 60s. They were working in Homedale, New Jersey at a lab there. They had a big horseshoe antenna, it's a horn antenna actually, and they were trying to work with early microwave transmissions, and they had this hiss, this background hiss coming from everywhere in space. No matter where they pointed the telescope to, they always got this hiss. They tried replacing circuitry, thinking there was a bad circuit or something. Some pigeons had roosted in it, and they had deposited a white dielectric substance inside, so they got the scrub brushes out there and cleaned it out. Ph.D. is cleaning out the dielectric substance. Think about that. Anyway, so nothing they were doing could fix it. And it turns out a guy named Dickey at Princeton was getting ready to start looking because the prediction was made as early as 1948 that there ought to be this relic background radiation from an early epoch in the universe, very redshifted, coming in. The thing is, the technology didn't exist in the 40s and 50s, but it did in the 60s. And Dickey knew that. And then he happened to meet one of these guys at a meeting, and he talked to what he was doing. He said, "What's the temperature?" And he said, 3 Kelvin. He said, "Whoa, that's it. What's what? That's it." And he scribbled down on a napkin, what was he talking about. They published it up in the Astrophysical Journal Letters early in 1965, and a dozen years later, Penzias and Wilson got the Nobel Prize in Physics for their work. They just completely stumbled across it. It's amazing how that happens sometimes. Well, this is a plot made with a combination of data, kind of an old plot now. This is frequency down here in gigahertz, and the intensive brightness here in ergs per square meter per second per stereo rate per hertz. Don't worry about that, it's not terribly important. And they have various data here with some error bars thrown in, and they're plotted up here. And you can see there's a pretty good fit, and the dot here is a fit to a 2.726 Kelvin blackbody curve. Everything radiates. Everything must have temperature above absolute zero. This 2.726 is 2.726 Celsius above absolute zero. In real temperatures, like minus 440-something degrees Fahrenheit. It's pretty cold. But this was taken as the proof of the Big Bang because this was predicted by the Big Bang theory and not the other model. So for the past 50 years, this has been the reason why people believe the Big Bang. Well, great model, great theory, one good prediction it made. However, there are different problems. For instance, in 1989, they launched this thing called COBE as a Cosmic Background Explorer. Some of the data I just showed you came from the COBE. And it was supposed to detect some fluctuations in the background. You see, the idea is the universe can't be perfectly smooth because, well, is the universe today perfectly smooth? Well, no, we got galaxies and planets and stars, and we got galaxies, stars, planets, and people, right? The universe is pretty clumpy. So the idea is the universe started off pretty smooth, but it had slight differences in density. Some places a little more dense than other places. And those slightly larger densities acted as gravitational seeds, attract matter around them to produce the structure we see in the universe. Now, you have to have a very fine-tuned universe. If it's too clumpy to start with, you end up with a bunch of black holes, and you don't have galaxies, stars, planets, and people. And if it's perfectly smooth, you don't get any condensation. You don't have galaxies, stars, planets, and people. So you see the knife edge you sort of have to deal with there. That's another issue I don't want to go into right now. But the whole thing was, back in the 70s and 80s, they predicted, based upon their theory of the Big Bang, how much clumpiness there ought to be to account for the structure in the universe. And that clumpiness and the density would show up as very slight temperature variations. Remember that 2.726 Kelvin? Well, there would be some parts that would be a little hotter and some parts a little cooler. So it would be kind of spotted with different temperatures. And they said the temperature fluctuations ought to be about 1 part in 10,000. That is, the temperature is roughly 3 Kelvin, then you ought to have differences of 3 10,000ths of a Kelvin degree. Pretty small, but they could detect that with COBE. Had to go in orbit around the Earth, above the Earth's atmosphere, to be able to measure this. So they sent this thing up for 2 years, surveyed the entire sky, and what they found out was that the background radiation was perfectly smooth. They did some very fancy statistical analysis, and later on, further experiments. We've done 2 others orbiting, WMAP, and since then the Planck probe. They've actually gone into space in 99 and 2009, every decade sending one up to improve upon it, and they confirmed those fluctuations. I was doubtful for it at first. What they found is 1 part in 100,000, not 1 part in 10,000. You see what's going on here? They made a prediction. that you should have temperature fluctuations on the order of 1 part in 10,000. The actual fluctuations were 1 part in 100,000. Now, the way I always understood science, it was always taught to me, you make a prediction. If your prediction fails when you do the test, then your theory failed, right? But since then, the last 20, 25 years, I've heard numerous people tell me, in print, they write that the measurements beautifully match the predictions. I was like, wait a minute, I got a better memory than that. don't insult my memory on this, all right? Well, here's what they did. The fix was they simply altered the model to fit the data. They said, okay, well, the fluctuations are 1 part in 100,000. We'll go back and we'll rejigger the model here. We'll get it to work out so that it predicts what we had. I used to give this example in my teaching. I said, you know, if I were to give you a test at the end of a class here to test how well you learn the material, it would be a pretty good test, but what if I gave you the answer before that? For instance, I'm going to give you a test at the end of the day here, all right, end of my time here. And there's going to be one question, pass, fail, one question, you got to get it right. The answer's 42. All right, everybody got that? Would you say the answer with me again? 42. All right, now if I gave the test at the end of this, how many of you would pass that test? Not a whole lot of hands going up, okay? What's the matter with the rest of you? Dumb as a sack of rocks? What's your problem, okay? Obviously, if you have any care at all, you have any intelligence at all, you're going to pass that test, aren't you? So if you slip the answers to the theory and ask the theory to then pass the test, well, obviously it's going to pass. That's not a test at all, is it? All you're doing is you're constraining your model. You're fitting the data. But don't tell me it's a prediction, because it was not. Clearly, it was not a prediction. Well, here's a more recent map of the background showing the entire sky. And you get red, the yellow, the green, to 2 shades of blue. And that's showing you how you have different temperature fluctuations. By the way, you can see some structure. There's a big thing running across here that shows higher than temperature than normal. That's called the axis of evil. It's not just George Bush, but this is actually in physics and in cosmology. And that axis of evil has no explanation. They don't know why it's there. And pardon? Because it's not supposed to be there. It just messes the whole theory up. And most cosmologists and astronomers ignore it. They say it's there, but they can't explain it, so it must not be terribly important. By the way, it lines up with the solar system pretty well, which is interesting. This lines up with the Earth pretty well, but that's for another time. All right, so here's even more. That was the one I just showed you was a W map from about 15 years ago, and this is about 5 years ago, the Planck. And again, the axis of evil. It's there. It's real. But nobody has a clue what it means. I suggest that it might be telling us that this really isn't cosmic at all. There are other problems with the Big Bang model. We have what's called a horizon problem. This is the idea that the temperature is the same in every direction. I'm going to sit here at the center of the universe. I'm going to look off at point A, and I see this radiation coming. Now, that radiation from the background radiation supposedly emanates from 380,000 years after the Big Bang. Big Bang is 13.8 billion years ago. So at a good approximation, that's 13.8 billion light years away, isn't it? So photons of light are coming from 13.8 billion light years away at point A, and they're just now getting to me right here. But you got point B over here diametrically opposite to point A, and the radiation's been traveling for 13.8 billion years, just now getting to where I am now. Now, if radiation from point A is just now getting to where I am now, and from point B, radiation is just getting to where I am now, has radiation from A ever gotten to B, or from B ever gotten to A? No, couldn't have, right? But yet they're precisely the same temperature. Now, do that for 2 points in this direction, and that, pick any 2 directions you want, you know. You get the same within 1 part in 100,000. That's indeed a mystery. The entire universe has the same temperature. Why? Generally, things only have the same temperature if they've come in thermal contact and able to exchange heat with one another. In physics, the way we talk about it is if you want to see if object A and B have the same temperature or different temperature, you bring them to thermal contact, touch them together, you watch what happens. If heat flows from A to B, what do you know? A is hotter than B. If it flows from B to A, what do you know? B is hotter than A. It's called the 0th law of thermodynamics, by the way. And then, if there's no more heat flow, what do you know? Same temperature. Gee, they came in thermal contact, but A and B have never been in thermal contact. So why are they the same temperature? It seems like a very contrived universe, doesn't it? That's a problem. And then they also have what's called the flatness problem. There are different ways of looking at this. It has to do with geometry in the universe and such. I like to do it this way. I want to take the ratio of, we call it omega, Greek letter omega, just like the conference here, right? And it's a ratio of gravitational potential energy and kinetic energy of the universe. An interesting thing is that this ratio can be between 0 and any large number it could be. But the break-even point is 1. If the value starts out between 0 and 1, over billions of years, the value should go towards 0, identically. And if it starts off something a little more than 1, it should drive to very large values. After billions of years, you would not expect omega to be anywhere near 1. It should be 0 or just this huge number. Well, we've measured again and again and again and again, and it's always been suspiciously close to 1. But yet in a universe that's billions of years old, it ought not to be near 1. It ought to be 0 or very large. Why? Why is the universe so contrived in this manner? Well, back in the 1980s, they came up with a solution to this called cosmic inflation. It was developed in the early to late 80s, and it was devised to solve both these problems. The argument is when the universe happens, 13.8 billion years ago, the universe pops into existence, and it's not very big. We're talking like 10 to the minus 34 seconds after the Big Bang. That's 0.34 zeros or 33 zeros and a 1. That's a pretty short period of time, right? The universe pops into existence, then 10 to the minus 34 seconds later, the universe goes through this very fast expansion, far, far, far faster than the speed of light. In a very tiny, tiny, tiny fraction of a second, the universe got much bigger than it used to be. And then normal expansion takes off after that, like we see it has been for 13.8 billion years since then. Now the idea is this. You can allow the entire universe to come in thermal contact and come to one temperature in that little tiny fraction of a second, and then the universe is yanked out of thermal contact, and since then it's just now starting to reestablish. Furthermore, the value of omega gets pushed almost identically to 1, whatever its value is. It gets shoved so close to 1, like it's going to be like 0.9999 or 1.000, followed like 170,000 zeros or something. And after billions of years, it's barely backed away from the value of 1. Kind of magical how that happens, right? So inflation was far faster than light, and the thing is, there is no evidence for this. They tried to jump the gun a couple of years ago and say they found evidence, but very quickly that was shown to be not the case. So the thing is, even though there's no evidence for this, cosmologists, astronomers, they all believe in cosmic inflation. It had to happen because we're here after all, right? How many times have you ever heard that from an evolutionist? You throw out problems and they say, well, we're here, aren't we? Well, yeah, it's called begging the question. It's also ad hoc, which means you're just making it up as you go along. Well, that's not what it means, but that's what it more or less means. It's not falsifiable either. It's not falsifiable. Change of the Big Bang, I haven't got time to talk about all these, but in the last 30 years, the expansion rate has changed. It used to be 50 kilometers per kilometers per second per megaparsec. Now it's about 80. That age changed. It used to be 16 to 18 billion years, but now since the last 10 years, it's been 13.8 billion years. It was 13.7 for a while. Dark matter was introduced. I like dark matter, but it's a real rescuing device. There's good evidence for it, but on the other hand, it's a rescuing device they've invoked in cosmology to try to save things. A cosmological constant was something that Einstein came up with nearly 100 years ago, and it was kicked to the curb about 90 years ago, and it came back in the late 90s. They're now dragging and screaming the whole way. They call it dark energy now. I want to do a quick comparison with the Big Bang of 30 years ago. I was finishing up grad school about that time. And again, the expansion rate was different. There was no inflation. That was just being bantied about at that point. There was no dark matter. There was no dark energy. By the way, all of these things you wouldn't have put into a Big Bang model back then. You wouldn't think of leaving it out now, of course. There was no string theory. That's an idea about subatomic particles that has a lot to do with Big Bangs, it turns out. And yet, back 30 years ago, they had complete confidence in the theory. None of the things were included. Today, you would not dream of leaving those out, and they have complete confidence in the theory today. What will the theory look like in another 30 years? Well, I can be certain of two things. Number one, it won't look anything like today's model. And number two, they'll have complete confidence in the theory, won't they? All right, if history is any indicator at all. Does this start to look like epicycles? You remember that? The strength was all these epicycles you could add, and the weakness was all the epicycles you could add. So it starts to look like epicycles. How does this compare to Scripture? Does Scripture change? Does God change? No. So why would you want to take the changing ideas of man and interpret the unchanging Word of God in terms of those? Well, that's obviously wrong. It's obviously wrong. You should be examining man's ideas in terms of Scripture. Origin of the universe, some people see God. They say, well, what caused the universe must be God, but they're not paying attention because there are a lot of ideas. This idea of quantum fluctuations, that you get a little violation of the conservation of energy and the universe pops into existence. And this is really a misuse of quantum mechanics to do this. They argue that the universe has zero energy, and if it has zero energy, the universe could exist forever. There's several problems with this. Again, besides the misuse of quantum mechanics, there's pretty good evidence that the sum of the energy in the universe is demonstrably not zero. It's huge. So they make up these fields, potential energies that are negative. And usually potential energies are arbitrary in physics, but they say, no, these are real negatives. And it just so happens that these all balance out. All the positive energy and negative energy balance out. Well, there's no evidence for this. It's just an article of faith on their part. Ways to avoid a beginning. You have quantum fluctuations. You have a universe unbound in time. Stephen Hocking's been good on that. Rebound, that seems the universe bounces back and forth. You have an eternal universe again. Multiverse, that's a bizarre idea that came out about 25 years ago. I read some stuff on it at the time, but now it's mainline. People are talking about it very seriously out there. Baby foam universes all the time. I got two great quotes on the quantum fluctuations. One of these is, the universe is the ultimate free lunch. You heard it, free lunch does not exist. Well, that's pretty much what's going on here. And then the other, I love this next one. The universe is just one of those things that happens from time to time. I mean, this is said a little tongue-in-cheek, but the humor only works if there's an element of truth to it, and they're basically admitting, yeah, this is a bizarre idea, but hey, it just happens. The universe happens. And they're deadly serious about, even with that quip behind all of that. Is the Big Bang biblical? Well, again, an event happened 13.8 billion years ago, and looks like to me like Scripture tells us the universe is just a few thousands of years old, doesn't it? Exodus 20:11 says the universe was made in 6 days. Many stars preceded the earth. You had stars forming for about 9 billion years before the earth came along. The earth is a Johnny-come-lately. But yet we know the stars were made on day 4, not on the earth on day 1. And also it's an ongoing process. The Big Bang's still going on. Evolution's like that. It's still ongoing. But we know from Genesis 2, 1, and 3 that it's a completed process. Where do you place the time? There are various places, day, age, allegory, all sorts of things like this. I've told people for years, at least 17, 18 years, that I'm intellectually open to the idea of billions of years. But the thing is, it has to be done in a biblically faithful fashion. I think I've seen every attempt to do that, and they all fall short. But if you think you got one I've not heard, I'll be glad to entertain what you have to say. But it's got to be biblically faithful, folks. Big Bang in the Bible, the direction of the research is atheistic. The people are trying to see God in this. They don't seem to notice that, or they ignore that. The time issue is huge. The order of creation is wrong. You know what? The beginning and the ending of the universe were sudden. In 2 Peter 3:10, it talks about the universe coming to a swift conclusion. I talked to one astronomer out there, a Christian fellow, name you probably know, who agreed with me. He even offered it before I even asked, that the universe will suddenly end. And I said to him, well, why don't you believe it began suddenly? Recently. And he isn't going to go there. It began suddenly, but that was billions of years ago. He doesn't see the asymmetry showing up there. And finally, when the Big Bang theory is abandoned, what becomes of our apologetics at that point? Remember, when the Roman Catholic Church endorsed the Ptolemaic model, we're still living with the millstone of that around our neck. And so in the Big Bang theory, if science is any teacher, it will go the way of the De Soto. And when it does, what does that do to our Christian apologetics? So it's changing, it's contrary to Scripture, and again, our apologetics is wrong. Very quickly, I know I'm out of time, We got a book table out there from Answers in Genesis. I do have 3 resources that I've written that I want you to know about. One's Universe by Design. It's a book about cosmology. I talk about the Big Bang like I talked about today, and much, much more. If you really want to learn more about it, that's probably the best resource I can recommend. I'm biased, though, being the author. We also have a book I wrote last year, a little pocket guide. We have 19 in our series. We only brought 3 with us on this trip. But the pocket guide on UFOs and ETs is almost 100 pages. We get this question a lot. We have a new planetarium show at the... How many people have been to the Creation Museum? Oh, very few of you. You need to come. We have a planetarium show we premiered last year on UFOs and ETs, and this goes in a lot of detail about that. And then finally, I want to tell you about the new astronomy book. It's a book I came out with a year and a half ago. It's part of a series. It's a color. It's beautifully illustrated, primarily intended as a kids resource. But I've had many adult friends of mine have read it and have really enjoyed it and gotten a lot out of it. It's not patronizing to the kids. There's a lot of material in there. It's also color-coded at 3 levels. If you do homeschooling, you can actually use this 3 different times at different age levels. So it's very appropriate for homeschooling. Well, I thank you for your attention, and I hope to see some of you more later on. Thanks for coming.